In recitation notes 3, there's a very useful table here that lets you solve any masses theorem problems. But when I first read it, I was quite confused by what this term was and why we had to make these comparisons with these strange arbitrary quantities. So here's an explanation on how that's derived. So we're trying to distinguish between the three cases. The first case is when the work done at the leaves at the bottom level dominates. So the bottom would be here. This is the bottom. This is top. So we're trying to see if top dominates, bottom dominates, or case 2, work is balanced. Well, the only way we could possibly do that is by comparing the work done at the top and the work done at the bottom. So we do bottom versus top. Well, what's the work done at the top? Well, if the recurrence relation looks like this, then the work done is clearly this term. And so the work done at the top node is n to the power of c. And for the bottom level, the work done across the whole layer is just the number of nodes, because the work done at each node is 1, it's the base case. So how many number of nodes are there? Well, it's a to the 0, e to the 1, a to the log b of n. So it's a to the log b of n. So now we just have to compare these two values. But hey, turns out it's hard. The one is in terms of a and one is in terms of n. Wouldn't it be nice if we could convert that term to have a different exponentiator? Well, I'm going to show you at the end of the video how that is done. But it turns out this value is exactly the same as n log to the b of a. So that looks familiar because that is exactly what they're talking about. They're saying if the work done at the leaves dominates, approximate p of n to just be the work done at the bottom. That's all they're saying. And the way you would know that is, n log b, because you're comparing these two values, and because they have the same exponent, you're comparing log b of a with c. So hence the conditions. If c is smaller than log b of a, then that's when you know this term asymptotically dominates. Likewise, you can infer the same for the rest of the cases. So that's all. Now for the last part of the video, you can just speed it up. I'm just going to prove why a to the log b of n is equal to n log b of a. Well, so I messed up the last time I tried to derive it, so this time I'm going to do it correctly. Let's start from the left side. That's just equal to, let's expand this part. So this is just log of so I could have chosen any base here. It's a change of base formula, and that would be valid. Then that's just equal to a to the log a of n to the log a of b. And the reason I did that is, imagine if it was 2 to the power of 3 over 2. Well, that's just equal to 2 to the power of 3 to the power of a half. Because you then multiply the top together to get 3 over 2. So that's what I've done on the next step. Alright, straight away we see this term becomes n, and we're getting very close. We're getting very close if you compare these two. Now, this is equal to 1 over log n of b. Wait, my bad. Let's try this one. I'm not sure whether this would work. Log b of a. Using the base of change formula again. Change of base formula again. And that would give us n over 1 over 1 over log b of a. And then we just invert that once more, and that becomes log b of a. And that's how we get that. So yeah, that's a proof of why a of log of b of n is n of log of b of a. And we do this, we go through that trouble, so it's easy to compare the work done at the bottom with the work done at the top. Great.